You're on a video call, a conversation that matters, a presentation, a catch-up with someone you haven't spoken to in a while. The connection hiccups. There's a half-second freeze, a brief scramble of pixels, and then the call picks up where it is now, not where it was. Nobody pressed pause. Nothing rewound or replayed. The missing moment is gone, and the call moved on as if it never happened. If you've spent any time thinking about how reliable networks work, the confirmations, the retransmissions, the waiting for missing pieces before advancing, this should feel strange. Where did the retry go? Where is the persistence that refuses to declare success until everything has arrived? Why did the system not wait for what it lost? The answer is that it chose not to, and understanding that choice reveals something about reliability that the standard framing leaves out. Reliability is a feature, not a universal good. For some applications, demanding it makes things worse. Imagine you're driving somewhere you have never been, following navigation directions on your phone. The app tells you to turn right in 200 meters. Somewhere in that instructions journey from server to screen, a packet goes missing. The app requests a retransmission. The retransmission arrives, but it takes 4 seconds. By then, you have already passed the turn. The instruction that arrives is not slightly imperfect, it is wrong, not because the data inside it is incorrect. The turn was real, the distance was accurate, but because it arrived at a moment when that information no longer applies. You are past the turning. The direction is now a fiction. In that situation, the retransmission did not help. It actively misled. The navigation app would have served you better by skipping the missing packet entirely and moving to whatever reflects where you actually are, rather than faithfully recovering a piece of information that the passage of time had already made useless. Here is the insight in one sentence. For real-time applications, a packet that arrives late is not a slow success. It is a different kind of failure. This is the trade-off that reliable delivery cannot resolve on its own. Reliability guarantees completeness. It ensures that everything sent will eventually arrive, but it says nothing about timeliness. A retransmitted packet arrives when it arrives, after the round trip, after the timeout, after whatever delay the network introduced. And for applications whose value depends entirely on what is happening right now, a complete answer that arrives late is less useful than an incomplete answer that arrived on time. Video calls are the clearest example. Each frame of video is a snapshot of a moment. By the time a lost frame has been requested, retransmitted, and delivered, several more frames have already been generated. Inserting the recovered frame at that point would not repair the stream. It would mean showing the past after the present has already played, creating a stutter that feels worse than the original loss. The right response is to discard the missing frame and keep playing from where the stream actually is. The same logic applies to voice calls, where a recovered audio packet arriving hundreds of milliseconds late produces the wrong sound at the wrong time. To online games, where a player's position from half a second ago is not where they are now. To live sensor feeds, financial ticks, real-time telemetry of any kind, anything where the data carries an expiry time measured in milliseconds. The protocol built for exactly this purpose is UDP, User Datagram Protocol. The most accurate description of it is that it sends packets and does not ask what happened to them. No connection setup, no acknowledgements, no retransmissions, no ordering guarantee, no confirmation of any kind that anything arrived. What UDP provides is speed and simplicity of a specific kind. A packet goes out immediately, without a handshake. It travels without generating confirmation traffic in return. It arrives, or it does not, and the sender moves on either way. This sounds like a failure mode. For a file transfer, a database query, or a web page, it would be. But for a live video stream, UDP's absence of guarantees is not a weakness. It is the correct match between protocol and application. The stream does not need completeness. It needs timeliness. and timeliness is the one thing reliability cannot give it. UDP is why your video call skips a frozen frame rather than waiting for it, why a live audio stream crackles briefly rather than buffering, why DNS lookups, which need to be fast and can retry the entire request if no answer arrives, do not carry the overhead of a full connection. The applications that use UDP have decided, correctly, that the cost of reliability exceeds the value of the losses it prevents. The picture is not as binary as TCP versus UDP, and that is where it gets more interesting. Many real-world applications need something in between. A video call, for instance, might want reliable delivery for the call setup, the negotiation, the metadata, the signaling that establishes what codec to use, while sending the actual audio and video frames without any delivery guarantee at all. The two requirements coexist in the same application, and they call for different handling. This is part of what QUIC was designed to address. Built on top of UDP, but implementing selective reliability in software, QUIC allows different streams within the same connection to carry different delivery guarantees. A stream handling critical metadata can require confirmation and retransmit on silence. A stream carrying live media can send and move on. And a loss on one stream does not stall the others. The head-of-line blocking that reliable connections impose does not propagate across independent QUIC streams. Each stream handles its own losses without freezing the rest. The same principle appears throughout modern protocol design. WebRTC, which powers browser-based calling, uses UDP as its foundation and leaves recovery decisions to the application layer. Game engines implement selective retransmission in their own code, retrying inputs that must be processed in order, discarding position updates that have been superseded before they could arrive. What ties all of this together is a question that reliable protocols do not ask. Does this piece of data still matter by the time it arrives? For a file, the answer is always yes. Every byte is part of the whole, and the whole is only complete when nothing is missing. For a live video frame, the answer changes the moment the next frame is generated. For a DNS response, the answer changes the moment the application times out and asks again. For a game state update, the answer changes with every tick of the game clock. Reliability is the right answer when completeness matters more than timing. It is the wrong answer when timing matters more than completeness. The engineering challenge is knowing which one you are building for and reaching for the right tool. A network that always retries is not more reliable in any useful sense. It is more complete, which is a different thing entirely. The most reliable video call is not the one that recovers every lost frame. It is the one that keeps moving, keeps playing, and lets the losses pass. Because what arrived on time is worth more than what arrived perfectly. Completeness and reliability are not the same promise. Knowing the difference is how you choose between them.